Hello, quick video on standard differentials of trig functions. We've done a lot of work in the first year on differentials of powers of x and polynomials, and it'd be really useful to know what the differentials of our standard trig functions sine, cos and tan are. And this video is going to go through and we'll just work them out quickly. Let's start by looking at the cosine function. Here we go. So let's use the graph to help us look at the differential. So when x is 0, we can see here that our gradient, because that's what our differential is 0, isn't it? So I can just mark that point there for that one there. When we reach x equals pi over 2 at this point here, we could very quickly have a look at what the gradient is here. So let's do that. Quite quick gradient line here, shall we? Just drop it in there as a tangent. So there's our little tangent line, yeah? And if we just moved that along a bit so that we could see what it's doing against our little square here. So here's a little square. Let's just do that there. Okay, we just came down from the 1.5 down here and then across. We'd see, there we go, that it's gone down a half there and it's gone across a half. So the gradient here, well, gradient here is -1 here. So let's mark that point. So at x is pi over 2, the gradient is -1. If we then went to this point here, that's pi equals, so that x equals pi, and the gradient here again is 0, so I can mark a point there for my gradient curve. And if we get to 3 pi over 2 here, you can probably see that through symmetry with what we were doing over here, the gradient here is +1. So I can mark that there, +1. And by the time we get to x equals pi, we're back here to having a 0 gradient. So there we are. That's the sort of our points, and we can see that it's coming around smoothly around. So let's just draw in a curve, smoothed in curve. What we've just looked at. There we go. So it's not very good, that little section in the middle, is it? Let's go and do that bit again. So just make it a bit smoother there. And what we can see here is, well, that looks awfully like a sine curve, doesn't it? Starting at 0, it's the sine curve. So if I dotted line the sine curve, the only difference here we're looking at is that the values are all the negatives values of the sine curve, yeah, because it's all been reflected around the x-axis. So we can therefore see, just look at that visually, that for y equals cos of x, the differential is minus the sine of x. Yeah. We could also have a look at that. We could also prove this using a unit circle, using a graphical solution. Yeah. So here's a unit circle. It's got a radius of 1. We've got an angle there in the red of an angle x. And there's our triangle, isn't there? So the base of the triangle here is going to be cos of x. There we go. It's got that distance there, the base of the triangle. By definition of trig functions is cos of x, because the hypotenuse is 1. Okay. Now if I increase the angle by a little delta x here, I end up heading around the arc. There we go. And that distance there will have gone round is r delta theta. So that's going to be our, in this case, our hypotenuse is going to be 1 times delta x, because that's our angle. So that distance is delta x, yeah. And if we looked at we can see that this blue triangle here is actually a similar triangle to the big red one. And therefore our angle's the same as x in this little triangle. So the opposite side is going to be our hypotenuse times by the sine of x, yeah? So we can see that our point P is moved around to this new P dash point, and our cosine, which was cos of x, has got slightly shorter, hasn't it? And the distance it's got shorter is delta x times sine of x, yeah? So therefore we can see quite quickly that our change in cos of x is minus delta x sine x. And if we divide that by delta x and then limit delta x to 0, we see that we've got this relationship at the bottom, that the differential of cos of x is minus sine of x. So that will make sense with what we saw at the graph. Okay, now we can speed up a bit because the sine curve's going to look awfully similar here. So there's our sine curve, our initial gradient here at x equals 0. If we drew the line on again, we'd find that our gradient was 1. So we're starting with a gradient of 1 when x equals 0. When x is pi over 2, there we go. Our gradient is 0. It's horizontal, isn't it, that curve at that point? So it's going through y equals 0. When we get to x here, at this point here, that x equals pi, our gradient is minus 1, as we saw in the cos, so there it is down there. And when we get to x is pi over 3 pi over 2, our gradient's gone back to 0, so our point's there. And when x is up again to pi, here we go, our gradient's back to 1. There we go. So again, if we just drew through this smoothed out curve, we would find we've got a curve here that looks like the cosine curve, doesn't it? And that's exactly what it is. So there we are. So we now know that if y is sine of x, the differential of sine of x is cos of x. Again, we can prove that graphically, following the sort of line we did just now. Here's our unit circle, and the vertical side of the red triangle is sine of x. If we increase our angle by a small amount delta x, and we create our mini triangle, and our sine of x increases, and again our hypotenuse is r delta theta, which is going to be r theta, which is 1 times delta x, and this is going to be the adjacent side, so that's delta x times cos of x. And therefore we have this differential expression here, that our small change in sine of x equals delta x times cos of x. And therefore if we divide by delta x and we limit delta x to dx to delta x to 0, then we find the differential of sine of x is cos of x, which is what we're expecting. So we now know the differentials of sine of x and cos of x. How can we use that for tan of x? Well, it's not so easy to do graphically, but let's just have a quick look at this using identities. Well, there's an identity that the tan of x equals the sine of x over the cosine of x. And we could see here that we could use the quotient rule to differentiate this. Separate videos on that. So if u equals the sine of x, then the differential du by dx is cos x, and if e is the cos of x, then dv by dx is minus sine of x. And if we put that into the standard formula here for the product rule, then we'll get dy by dx is v cos of x times du by dx is cos of x minus the sine of x times the differential of the dv by dx is minus sine of x. So what we can see is that we end up with cos squared plus sine squared on the top, and the denominator becomes cos squared of x. Well, we know that cos squared plus sine squared always equals 1, so we now know that the differential of tan of x, dy by dx, is 1 over cos squared of x. And if we have a quick look at this graph here, the green line is our tan line here. So when x equals 0, our gradient, again, if we looked at it, is roughly 1. So that's that point here. Here's our black line, is our differential line, and then the gradient's positive on both sides, and the curves are rotationally symmetric. So here we get this curve here, and that's 1 over cos squared of x. So we can see that that all works, can't we? So there we are. Here are 3 standard trig ratios and their differentials. Yeah, cos of x differentiates to minus sine of x. Sine of x differentiates to cos of x, and tan of x differentiates to 1 over cos squared of x. I hope that's of use.